So in this lecture, we'll be looking at the lubrication approximation. I'll be laying down the ground for problems in thin films. But before we look at problems in thin films as in interfacial flows, we'll look at some classical problems in lubrication approximation or thin gap approximation in this lecture. So one of the common problems that one comes to mind when one studies lubrication approximation is the problem of a journal bearing. Here I've made a sketch of a journal bearing. And you can see that the journal bearing has mainly three parts. You have the housing here, and then you have a rotating shaft in the middle, and between the rotating shaft and the housing you have a blue region which is the oil. It could be any other lubricant. Now the common lubricant that we use in industrial processes is some kind of an oil, so I've called it oil. Now notice that the shaft and the housing are not concentric to each other. The gap actually reduces as the fluid is squeezed. As the shaft rotates, the fluid is squeezed into this narrow gap, and as the fluid is squeezed into this gap, the fluid offers resistance to motion because of viscous forces, and this leads to buildup of pressure, which we call as lubrication pressure. Now lubrication pressure, the textbook example, apart from the journal bearing example, the textbook example would be a wedge where you have let's say the wedge is moving from right to left, and as the wedge moves from right to left, the fluid basically gets squeezed into this narrow gap, and that leads to buildup of pressure. And this buildup of pressure is very important because that's what supports the load. Lubrication approximations also occur in common other common problems, day-to-day life problems. For example, if you take a sphere or a ball and move it against a substrate, just before impact, you'll have a scenario as depicted. The ball is about to touch the surface, and before it makes contact with the surface, the gas that is around the ball, especially beneath the ball, has to be squeezed out. So sometimes these are also called as squeezing flow problems. Okay, they all have a common feature, squeezing flow problems, lubrication problems, in that the pressure in the thin gap becomes very large. So the subject of this lecture is what is called as a lubrication approximation. I'll also tell you why do we call it as an approximation. This is sometimes, you can also call it as a thin gap approximation. Primarily because this kind of a problem, lubrication, occurs when you have a thin gap geometry. So let's look at the basic setup of this problem, and the goal of this lecture is to derive the governing equations for the lubrication approximation. Right? So I have first considered a general setting. This is a 2D setting, a general two-dimensional setting where you have a bottom surface which is flat, and then you have a top surface which is moving in an arbitrary direction with an arbitrary velocity. So at each point on the surface you have a velocity x and y. So the surface can also be evolving, but if you say that the surface is a rigid surface, then the velocity will be constant for the entire surface. So we'll consider the case of a rigid surface. Further, we will say that the thin gap is given by the equation y equals h of x comma t, meaning the thin gap is varying in space, and there is a characteristic thickness for this thin gap, which we call it as h, and the characteristic horizontal length scale is L, right? Now, in the case of the ball that is falling, the horizontal length scale could be something like the curvature of the ball, whereas the vertical length scale, the thickness of the gap, could be something like the thickness of the gas layer. And in the case of the lubrication, the problem in the journal bearing, the diameter or the radius of the shaft could be like the horizontal length scale, or it could even be the curvature. And whereas the thickness of the gap could be something like the characteristic thickness h. So our goal is to derive the lubrication equations. So I've already written down the Navier-Stokes equations for this 2D problem. So this Navier-Stokes equation is for this fluid whose viscosity is mu and density is rho. And for this fluid, we are assuming that the fluid is incompressible in Newtonian. And I've written down the Navier-Stokes equations for this. Notice that I have put a small tilde for all the dimensional quantities. So the velocity, the length scales, x and y, and the pressure all have a tilde on top. So these quantities with the tilde, they are dimensional quantities, right? Now the first step is we will non-dimensionalize this problem. Now to non-dimensionalize it, we will pick a bunch of characteristic scales. So what are the relevant characteristic scales? So in horizontal, L is the horizontal scale, H is the vertical scale. That's vertical scale is basically the characteristic scale for the thickness. U naught is velocity scale. Horizontal. We'll say V naught is the vertical velocity scale in the vertical. And since pressure is one of the most important quantities, the scale for pressure is most important quantity in lubrication problems, and we don't know what is the value of it, we will call it as PC, which is pressure scale, the characteristic scale for pressure. Now using all these characteristic scales, let's write down the non-dimensional variables first. So x star, or let's call it as x and y, would be x tilde by L and y tilde by H. U and V, the horizontal, non-dimensional horizontal and vertical velocity would be U tilde by U naught and V tilde by V naught. The characteristic scale for time will be T tilde divided by L by U naught, and the characteristic scale for pressure would be P tilde by PC. Note that PC is still unknown. So we have V naught and PC both unknowns. Now what we will do is substitute these non-dimensional variables into the governing equations, which is basically these equations that you see on your screen, and then we will get a bunch of non-dimensional numbers. Now before we do that, we have not yet defined what is the lubrication approximation. Now if you notice here, this is the sketch that I've made. I have a horizontal length L and a vertical height h. The lubrication, I'll call it as the lubrication limit or the lubrication approximation, is when you have h by L is very, very small. So the thickness is much smaller than the horizontal width. In other words, we will define a parameter epsilon, which is h by L, and we say that this parameter is very small. Okay. Now we will see how this parameter naturally enters our non-dimensionalization. Let's start with the continuity equation. Now for the continuity equation, we have del u by del x plus del v by del y, all with tildes, is 0. And this immediately translates to u naught by L del u by del x plus v naught by h del v by del y is 0. Now the scale of this term is u naught by L, and the scale of this term, the second term, is v naught by L, v naught by h. So if I balance these two terms, we need to balance these terms for mass balance, and therefore we require v naught by h should scale with u naught by L, and therefore v naught should be something like epsilon u naught, where epsilon is h by L. So I can now choose, we can now choose or set v naught to be epsilon u naught. And notice that if epsilon is very, very small, which means that if you are in a thin gap geometry or in the lubrication approximation, v naught is much, much smaller than u naught. So which means that most of the velocity is parallel to the surface or in the horizontal direction. The vertical velocity magnitude that is perpendicular to the surface is very small. Now let's look at the x momentum equation. I'll directly write down the x momentum equation without writing down the dimensional equation. So if I substitute the x momentum equation, the left hand side here, that's the inertial terms, they all become density times u0 square by L. What we now have is del u by del t del x. That's the inertial terms. The scale for pressure is unknown, but what we get is Pc by L del P by del X. And now you have mu. Let's look at the two viscous terms. You have del square U by del X square, and this term becomes the magnitude of this term is comparable to U naught by L square. So what we have is U naught by L square del square U by del X square plus u naught by h square del square u by del y square, right? And now what we can do is we can notice that we can simplify this a little bit. Notice that this term, the size of the viscous term, this is mu del square u by del x square, correct? the scale of this term is mu u naught by L square. The second term corresponds to mu del square u tilde by del y square, and the scale of this term is mu u naught by h square. And clearly, because h is very small compared to L, clearly the right hand side term, the second term, is much larger than the first term, which means that the viscous stresses in the vertical direction are much larger than because of the horizontal direction. So in other words, the second term, del square u by del y square, they are the shear stresses. Del square u by del x square, they will correspond to the normal stresses, right? You can further simplify this by writing down the equation as rho u naught square by L. I will simply write this as du by dt, which is the material of the substantial derivative, is minus Pc by L del P by del X plus mu, I will take this out, epsilon square L square. What I now have is epsilon square del square u by del x square. That's a first viscous term, and then I have del square u by del y square. Notice that I have again used the definition of epsilon to replace h square with epsilon square L square. So clearly you can see that I have an epsilon square sitting in front of the first viscous term, and because it is very small, if epsilon is very small, that term is very small. Now let's rearrange this equation, or maybe what we will now do is to look at the scale for pressure. The characteristic scale for pressure. So we have two options. If inertia is important, then what we have is we balance the pressure term, that's the size of the pressure term, has to be balanced with the inertial term, because inertia is much larger than viscous term, and therefore pressure has to balance with whichever is the largest term. And what we get is the well-known result for pressure, which is rho u naught square. This is what you would get, for example, even in the Bernoulli's equation. If you're in the viscous dominated regime, then the scale for pressure in this case, Pc by L, would scale with the largest viscous term that is present, which is mu u naught by epsilon square L square. Okay, and therefore I get the scale for pressure will be mu u naught by epsilon square times L. Right? So I have two scales for pressure. Now we anticipate that we are in the lubrication problems. The pressure is one of the most important ones, and pressure is what supports the load. Further, by thin gap approximation, we are also saying that the Reynolds number is small, and I will explain in what sense is Reynolds number small, or in what sense is the inertial term not very important in these problems in a few minutes. So we will choose the second scale for pressure, and if we substitute the scale for pressure, then we can simplify these equations further. Now I want you to try and do this analysis yourself. Notice that the viscous term is del square u by del y square. That's the second term on the right hand side. Okay. We have balanced the scale, pressure scale. We have balanced these two terms. We have balanced the pressure term with the viscous terms. So both of them will be of the same size, and in fact they will be order 1 terms. So what we now have is del square u by del y square minus del p by del x. This is equal to minus epsilon square del square u by del x square. I've taken all the other terms, all the order 1 terms on the left side. There are only 2 of them. And all the other terms will be on the right hand side. We have epsilon square Reynolds times du by dt. This is the non-dimensional x momentum equation. Alright. Now we will similarly consider the y momentum equation. So the y momentum equation, again we already have the scale for the pressure. We have the scale for the velocities. Now if we do this analysis, what do we get? If we do the similar substitution, then we are going to get, I'm not going to derive this step by step, but if you were to do this, then you will get epsilon square that's the viscous term, and then we are going to get epsilon Reynolds. This is the non-dimensional y momentum equation. Continuity equation, we have already seen it, but we have not written down the non-dimensional form. This simply becomes del u by del x plus del v by del y is 0. This is a continuity equation. Now what you see on the screen are 3 equations which fully describe the problem, but the only difference is that these are in the non-dimensional form. Now we are going to exploit the lubrication approximation. So by lubrication approximation, if you notice here, there are 2 parameters in the problem. There are 2 non-dimensional parameters. Relevant to this problem, that is epsilon square and epsilon, or rather you can just say epsilon and epsilon square Reynolds number. Though the non-dimensional parameter is indeed epsilon square, but epsilon and epsilon square Reynolds number are the relevant non-dimensional terms. Now we already know that epsilon is very, very small. We also set epsilon square Reynolds number is very, very small. So in practice what we would do is we would say the Reynolds number is fixed, but the product of epsilon square with Reynolds number makes this term very, very small. So in general, we can keep RE fixed and consider the limit epsilon power n times Reynolds number goes to 0 as epsilon goes to 0. So in other words, the very fact that epsilon is a geometrical parameter, when epsilon goes to 0, inertial terms drop out. Okay. And note the inertial terms in the x momentum equation appear with epsilon square Reynolds number, and similarly the inertial terms in the y momentum equation, anyway they're multiplied by, in fact they're multiplied by epsilon power 4, right? So how do we now go about simplifying these equations with this? We simplify this equation by basically taking an expansion. So we can say u in the non-dimensional form, which is a function of x, y, and t. This is some u naught. That's the leading order u naught. I will not, it's understood that it's a function of x, y, and t, plus some unknown gauge function of epsilon times u1 plus so on. Similarly, v can also be expanded in the similar fashion, but some other unknown notice that the coefficient of the first term on the right hand side, that is u naught, v naught, and p naught, the coefficients are all unity. That is because these terms have to satisfy the boundary conditions. So these are referred to as leading order terms, and subsequently these are referred to as first order. Sometimes the leading order terms are also called as zeroth order. Okay. Now, if I were to substitute these expansions into these equations and only retain the leading order terms, we get what are called as the leading order equations. So we substitute these expansions into the non-dimensional equations to get, so the leading order continuity equation just simply becomes the following. The leading order x momentum equation. Now notice that all the epsilon terms will drop out. Then the right hand side are the epsilon terms. We have del square u by del y square del x is 0, and finally the pressure term is basically in the y momentum equation is simply this. Okay, so these equations are collectively called the lubrication equations. We can write down the necessary boundary conditions for these lubrication equations. You can set the boundary condition at y equal to 0, which is the no slip condition at the walls. You have u equal to 0 and v equal to 0. That's the no slip and the no penetration condition. And at y equals h of x comma t, that is on the upper surface, you have u0 as capital U and v0 as capital V. So with this, one should be able to solve the system of equations. And notice that you can integrate the x momentum equation directly to get the velocity that's varying in y. And once you know the velocity field, you can then use the continuity equation to get the vertical velocity and also get the pressure field. Now I want to make one important observation about the pressure. The pressure and lubrication problems, if you notice, the characteristic scale for pressure was mu u naught by L times an epsilon square. That was the scale for pressure that we obtained here, mu u naught by epsilon square L. So what do we see is that the pressure scale in lubrication problems, in lubrication or thin gap geometry problems, the pressure scale is an order 1 by epsilon square times larger than the characteristic scale characteristic viscous scale for pressure, which is just mu u naught by L. In other words, just by taking a lubrication geometry or a thin gap geometry, the pressure, the characteristic scale for pressure is 1 by, you have this 1 by epsilon square. The pressure gets enhanced significantly. This is the very reason why engineers exploit this thin gap geometry to provide lubrication. Now, one of the other important simplifications that we've done in this analysis is look at the geometry. We have walls on both sides. You have a wall at the bottom which I've taken to be flat, but it could be any other shape. And you have a wall at the top, which is in this case a wavy wall. But the position of the walls is prescribed. It's fully prescribed by the velocity field and the thickness. The thickness itself, h of x comma t. Why did I say h of x comma t? Because if the wall is moving to horizontally or vertically up, then the thickness at any given point is changing. But apart from that, the position of the wall is fully determined by the problem. It's given to the user. You know a priori what is the position of the wall when you solve these problems. But if you were to replace the upper surface with an interface between two fluids, let's say for example you have a thin film flowing down an inclined plane, the shape of the thin film has to be determined. The location of the interface has to be determined as part of the solution. Now the boundary conditions that we applied at the upper wall was just the no slip condition and the no penetration condition. But the moment we take it to be an interface, then we will have to apply the normal stress balance and the tangent stress balance conditions at the interface. That's the subject of our next lecture. Thank you.